two goals today. One is to finish the argument we started last time, and so now actually is when most of the interesting things in the proof will happen. And the second goal is to justify the title of the lectures. We'll give a dictionary. So if you followed what happened here for these linear programs, so these polyhedral lifts, then we'll give a dictionary to convert the arguments for the polyhedral setting to the setting of semi-definite programs. I mean, and that's one of the main advents of this style of argument, that it seems quite powerful, and there is a very nice correspondence between linear programs and semi-definite programs. Okay, so now I have to remind you all where we were yesterday. Okay, so we had some non-negative function g, which think of this g as this g is non-negative on the hypercube in m dimensions, and but it's hard for juntas to certify that it's non-negative. So okay, so let's define d to be, let's say, the junta degree of g minus 1. Okay, so the junta degree of g is bigger than d by definition, and therefore what it means is that g cannot be written as a non-negative combination of functions that are non-negative and depend on only d coordinates. So the non-negativity of g is somehow, it's a bit global. It can't be just described by looking at d coordinates at a time. And we said that there's a universal way to prove that the junta degree of g is bigger than d, and that's by the existence of what we call a d locally positive function. So this implies that there exists this function which pretends to be positive on d juntas. Okay, so such that if we average over all x in 0, 1 to the m, phi x, qx, then this is non-negative for all d juntas that are non-negative. Okay, so when we average against this phi with a non-negative d junta, we get something positive. Okay, so the point is that these things cannot somehow realize that that this is taking negative values. But the point is that G does see that property. But phi x, gx is less than 0. Okay, so this phi is a separation between G and the cone of non-negative d juntas. Okay, so that was the basic setup, and then we, based on this, we now define the matrix. So the matrix is it's a non-negative matrix where the dimensions are n choose m and 2 to the n, and it's defined in the following way. So it's indexed by sets and by elements of the n-dimensional hypercube, and it's just defined as the evaluation of G at x, but x is an n-dimensional vector, so we just restrict to the coordinates in the set S, because G is a function on m bits. So this is for S, which is a subset of 1 to n, size m, and x in 0, 1 to the n. So we start with a function which is hard to, whose non-negativity cannot be certified by small juntas. We define this matrix, and now our goal was to prove that the non-negative rank of this matrix is large. And the reason for that is that this occurs as a submatrix. Okay, well, sorry. If G is quadratic, then this occurs as a submatrix of the slack matrix of the cut polytope, and therefore a non-negative rank lower bound on this matrix gives what we've been trying to get the whole time, a lower bound on the size of an extended formulation for the cut polytope. So now we define this thing, and now our goal is to prove a lower bound on the rank of this matrix. This is we're on the non-negative rank. Sorry. So let's okay. So let's do it now. Let's define R to be the non-negative rank. And the one nice thing about the problem session yesterday was, we were trying to come up with some extended formulation for a polytope, and there were many suggestions. We pursued for a while a path which didn't quite work out. But you see that, these extended formulations, they're quite, right? Like, so we were doing something with the subtor elimination polytope. So we said at some point, let's introduce some assignment variables for sort of like for an assignment relaxation, and then we played with these for a while. But you can imagine, there's a seemingly infinite number of different ways you could try to write an extended formulation. So it's seems to be a very rich model. So just it's okay. So sort of like it's this is a good exercise to see that it's okay. We should feel a bit proud of ourselves if we manage to prove some lower bounds on the non-negative rank. Okay, yeah. So if we know this, let me remind you what it means. It means that we can write the matrix in the following way: AI S BIX, where again these the AIs take sets of size m to non-negative numbers, and the BIs take elements of the discrete cube to non-negative numbers. Okay. And our goal now is to prove a lower bound on R, on the rank. And in fact, last time we even said how we're going to do it. So let me just remind you that if we write expectation sub S, then what it means is that S is a subset of size n chosen uniformly at random. And if we write expectation of X, we already wrote it, in fact. But it just means that we're taking X to be in the n-dimensional cube uniformly at random. So last time we said, and we had one more definition from last time, which is, we have, again, sort of, the idea here is that n is much larger than m. Think about it this way. G, the hard, sort of this hard function we start with, is only defined on m bits, and of course the proof, this locally positive functional, is defined on m bits. So we're just going to define, okay, I guess I should say the domain here. This functional on n bits is defined by phi s of x is just, we just restrict to the bits in the set S. Okay, so this is this is just phi, but it's moved to the set S. So if we want to prove something about G restricted to the set S, we should use this functional. Okay, and the strategy we said last time, what we're going to do is the following. Okay, so last time we proved two things. First of all, we proved that if we take, okay, we're gonna try to separate the two sides just by averaging them against some kernel. Kernel is just a word which doesn't mean anything. Okay, just by averaging them in this manner. And last time we said that if we do this here, this is less than 0. Okay, and the reason this is less than 0 is because it's actually, if you just unfold the definitions here, this is just this expression. This is an M. This is just this expression appearing at all the sets in S. Okay, so it's less than 0, so here it's also less than 0. And we said that if BI is a D junta, then this property of phi is going to imply that this is non-negative. Okay? So if every BI were d Junta, we would already have a, it actually doesn't matter even what R is, we would already have a contradiction because the right-hand side, well, when we apply this to the right-hand side, we would get something non-negative, to the left-hand side something negative. It's a contradiction. So we said that then our goal was now to approximate these things by Juntas, and then this optimistic sketch might go through. There's just one thing to note here that should leave everybody a bit uneasy. So if we try to, I mean, first of all, you see why averaging with respect to some kernel is a nice thing to do, because then we can just evaluate the right-hand side term by term. We don't even have to worry about the sum, right? Like just if we can prove that every term is positive against, when averaged against this kernel, then we separate the two sides. But what it means is that we have a matrix here. We're trying to separate it from some, say, family of matrices over here. But we're using a linear functional. So it means that in the back of our minds, we have, implicitly, there's defined a convex set where we're trying to prove that this matrix is not in that set. And if you just look at things this way, we're in a bit of a problematic situation because, it would be nice if we did something like, if we could do something like this. We would take, say, low non-negative rank matrices. This would give us some cone, and then we would be trying to prove via some linear separator that this matrix is not in the cone. The problem is that if you take the convex Hall of all the non-negative, like all of the low non-negative rank matrices, in fact, even if you take the convex Hall of all the rank 1 non-negative matrices, you get all the non-negative matrices. Okay, just because a matrix with a single non-negative entry is a rank 1 non-negative matrix. Now you could just sum up all these things. So the point is, this can't possibly work as is. So what we need to just do one thing to, and the reason is, of course, that we haven't used the fact that we have assumed that R is small, that we have a bound on R. So we're going to now do, but somehow this setting, we would really like to do this because this setting is so, it's such a nice way to prove things by averaging. There's like, in particular, there's all kinds of things, you can maybe afford small errors, and again, if we could get ourselves in this situation, and we could just sort of analyze this thing term by term. Okay, so now we're just going to do something very, so now is where we're going to use the fact that the rank is small, and kind of almost a very simple step. So let's do it. So the first thing, let's without loss of generality, we can assume that the average of BI is 1. Okay, this holds for every I. That's just by rescaling here. So you can scale the BI by some number so that this holds, and then just scale the corresponding AI by the inverse of that number so that this expression remains the same. So this is just to have some, I'm going to think about each of these BIs as actually a probability measure. In this case, a probability density with respect to the uniform measure. And then what I want to say is that basically that we can assume that the L infinity norm of BI, so I'll just define it here, just once we have this scaling, the maximum BI is positive, so I want to say that we can assume that this is small. Okay. And then once we're able to assume that this infinity norm is small, we're going to be able to forget the number of elements in this sum. So we'll forget R. So we're going to use the fact that R is small to justify this line here, and then we'll be able to forget the number of summands and just really analyze them one by one. Okay, so and the reason is just very simple. So let's say if the L infinity norm of bi is bigger than tau is just some parameter, then it implies that AI is at most, the maximum value of G divided by tau for every set S. Okay? And the reason is just that, look at this expression, everything on the right is non-negative. So if there's some value, if there's some x at which this is bigger than tau, all of these things must be at most the maximum of the left-hand side divided by tau. Okay? And the left-hand side is just evaluations of G. So if you remember with the proof, G is sort of fixed. So and the proof is and the statement we're going to prove about the non-negative rank will depend, in some arbitrary way on G. So you can think about this as, there's some constant depending on G, but this is really, but it's G is fixed. Okay. So the point is that so if some bi assumes a large value, then all of the AIs have to be small. Okay. And therefore their contribution. So what can be the contribution of such a pair to the expression we care about? So remember, we're trying to separate the two sides by averaging against this kernel. So let's take such a bi and just see what the contribution would be. So so we have this, and then we have we're going to average with respect to this phi s. Okay, so let's use the fact that these are all at most order 1 over tau. And so this is sort of at most order 1 over tau times the times the maximum value of this thing times so we're just the maximum value of this times 1 over tau, and then expectation of bi is 1. So that's the end of the thing, right? Okay, and again, remember that phi is something which is depending on G, but nothing else. So again, sort of the infinity norm of phi, we can take it to be a constant. So this is, let's say, order 1 over tau. Okay, so if we make tau really large, the contribution from these, from these non-smooth BIs, the one that takes large values, is very small. Okay, so we'll just so if we can do things very conservatively here. The only thing we have to worry about, of course, is that there's r of them, right? We have r terms, so if we if we lose 1 over tau, we might lose it r times if we did this. But if we set tau equals, say, r squared, then we can throw away these bad i's. Okay. Okay. This is not a mathematically rigorous statement, obviously, but it doesn't hurt. Okay. I don't want to carry around error terms throughout the arguments, but this is really, the point is that if we set tau to be r squared, then the total error we incur, even if we threw away every bi, is only order 1 over r. Okay. So, and if you think about r is going to be something, r is supposed to be something quite large. I should remind you the kind of lower bound we're trying to prove is that r is at least some constant times n to the d. So where d is the degree of g. So okay, so r is very, so this is like a, this error is very easily dealt with. Okay, so I'm just saying that the contribution from such terms to the to the kind of the expression we care about, which is this thing, is very tiny. Okay, so in fact, we said last time this is less than 0. How much less than 0 is this expression? Well, it's less than 0 by some amount depending on g. So okay, so there's some small epsilon depending on g. So we have the gap there, and well, as r goes to infinity, eventually the error we pay from doing this will be less than this gap. So we'll still get a separation even if we, we start with sort of a kind of a fat separation here. This is, this is some definite distance here. As long as this error is less than that separation, we're still getting a separation. Okay, So now I'm just going to assume that all of these are at most r squared. Okay, that's it. That was the use of the fact that the rank was small. So the point is now for the rest of the proof, we'll just analyze a single term and show that it's each term individually is non-negative. And now the number of terms in this sum don't matter anymore. Okay, so in communication complexity, if you think about it, this is sort of the usual. This trick corresponds to, if anybody's up on communication complexity, to only sort of having to worry about large rectangles, sort of because small rectangles are not contributing too much. Ignore this tangential comment. Okay, good. So now what's the setting we're in? I mean, what does it mean that these BIs have a small infinity norm? So I want to think about them as probability measures on the discrete cube. They're densities, but it's a positive function that averages to 1. And then the fact that they're not too big actually means that the underlying probability measure has very large entropy. Okay? So it implies, in fact, that the Shannon entropy, which we're not going to use it, so if you don't know the definition of Shannon entropy, it's fine. But for intuition, it implies that the Shannon entropy is n, which is the maximal entropy you can have for a distribution on n bits, achieved only by the uniform distribution, minus twice log r. And remember, again, r is n to the d. So this is like d times log n. So somehow this is very close to having full entropy. Okay, we're not gonna sort of use this. Instead, we're gonna use the relative entropy, which we'll just define. Okay, so maybe we should. Okay, let's keep this index. I'll keep the index I around so that you know where this bi came from. But from now on, we're basically just going to work with a single index, because as I said, we're just going to now prove that under this assumption, every one of these terms is almost positive, almost non-negative. Okay, but let's define this quantity. So it's just this is the relative entropy of bi with respect to the uniform distribution, but the definition is just this. Okay. It's an exercise to see that this is always positive, and you can also think about it. This is the entropy deficit of this probability distribution. So this is So in fact, we didn't say what is the Shannon entropy, but if you know what is the Shannon entropy, then I mean, this is the d we've just defined. It's how many bits we have as a deficit from being uniform, and then you can see just that since the expected value of bi is 1 and it's at most r squared, we know that this is at most 2 log r, just because every one of these log terms is at most 2 log r, and the average of this thing is 1. Okay, and so now the claim is going to be that for such high Shannon entropy functions, in some sense they're well approximated by juntas. Okay. So you can imagine how you can get a high entropy function. So here's what you can do. I mean, one way you can do it is look at some, say, if you look at some k of the bits and just fix them, and then let the distribution be uniform over the rest of the bits, then the entropy of this thing is n minus k. Okay? So that's a high entropy function, and the probability distribution is a junta. It only depends on what's in those k bits. The other n minus k bits are allowed to be free. Okay, so in some sense, this is going to be always true, although we have to be very careful because, okay, just as an example, consider the probability distribution, which is say uniform on strings such that the sum, such that the majority is 1. Okay, so consider this probability distribution. Okay, in fact, let's even make it, let's make it even harder. Okay, uniform on string such that the sum of the xi's is congruent to 0 mod 2. So the parity of the bits is even. Okay, so this is a, so first of all, somebody tell me how much entropy does this random variable have? Right. There's only one bit of entropy we give up here, which is just the parity of the bits. This is a very high entropy distribution, n minus 1. Clearly, though, it is not. You cannot. I mean, there's no sense in which there's a junta that's close to this thing. It's completely symmetric under permutations of the x's. So we will not be able to just say that something of high entropy can be approximated by a junta. Here's an example of very high entropy, n minus 1 bits of entropy. It's symmetric. There's no coordinate is any more special than any of the others. Okay, so our notion of approximation will have to be weaker than trying to get the function right pointwise. So now, I mean, it makes sense to see. Okay, so we want to do this approximation. What's the minimal thing we need from the approximator so that the argument still goes through? Okay? And you just see that the thing we're going to need from this approximator to make the argument work is that when we average, right, so we care about these averages, and our goal is sort of to use the fact that for juntas these things are non-negative. So what we care about is that these averages should be approximately the same for BI and whatever approximator we come up with. So for all the subsets, right? If we could get an approximation in this sense, then, okay, there's some error to worry about perhaps, but then the argument goes through. Sort of, if we would replace this expression by this expression, and now if these things are juntas, then we would get a non-negative contribution. Okay. So this is now, okay, so how do we construct this approximator? We're going to use convex optimization. This is a phenomenon that I guess I heard about for many years, but it didn't strike me, well, I didn't understand it, I guess, until we started working on these things. But so here's a convex optimization. So the first thing to notice is that this D, as a function on densities, so as a function on non-negative things with expectation 1, this is a convex function. Okay? It's just because x log x is a convex function as long as x's are positive. Okay? So we can minimize it on a convex set. So here's our method, going to be our method of constructing an approximation. So the variables of this convex program are going to be the bi tildes of x. We're going to have, there's 2 to the n variables. We're going to minimize the sort of the relative entropy. Okay. So if you think about this thing as a measure of complexity, then when the relative entropy is 0, it means that we have the uniform distribution. So you can think about it as some measure of complexity. The uniform distribution is the simplest one. And then as this thing gets larger and larger, the distributions are more and more complicated. So we're sort of minimizing the simplicity in this sense, subject to, well, the properties you expect. The expectation should be 1. This thing should be non-negative everywhere. And then let's impose these are linear constraints on the variables bi tilde x. So now we'll impose these constraints. And just here I wrote approximately the same as, actually, if you think about the proof, you only need one direction of this. So the proof is inequalities. So just you could write both here, but let's just write one direction. This is a band the kids like. One Direction. Probably didn't make it to Europe, seems. If it did, nobody is going to admit it, obviously. So, okay. Okay. Yeah. For all S, size M. Okay. Okay. So this is a convex program. Epsilon here is not a variable. It's just a parameter you can set depending on how accurate you want the approximation to be. Okay. So this is a. I mean, these are linear constraints on the BI tilde. So this is a convex set. We minimize the convex function over it. And so I'll tell you, okay. You could solve this to optimality, but actually the perhaps easier way in this setting to get some approximator which is simple is just to solve it by some sort of very naive form of gradient descent, which is just the following. You sort of start with some, okay, let's, okay, let me do it this way. Sort of, you start with the trivial approximator. So this is just a density which is just constant. So it's a uniform density. And then you come here and you look at, you have many constraints. You look at the constraints. You say, is one of them violated? If so, you try to move in the direction of that constraint. Okay. In this case, the one problem with sort of moving in the direction of that constraint is that, I mean, how do you move in the direction of the constraint? If this thing is, if this expression is too big, then you should move, you should move this thing to be the negative of this thing. The problem is that, this thing takes positive and negative values, and you need to stay in the set of probability densities. So you cannot just, so like if you just move around in space to satisfy some constraint, you could violate these constraints. So there is sort of a well-known, sort of commonly done thing, which is, goes by the name exponential weights or multiplicative weights update, which is that we won't move in this additive direction. We'll sort of move in some multiplicative direction so that we don't leave the simplex. And so you can do that until the constraint is satisfied. Then look if there's another violated constraint. If there is, move in the direction of that constraint. And you can keep doing this. And what you might worry about is that as you satisfy some constraints, other constraints suddenly that you satisfied previously have become violated. But what it turns out is that there's a global, okay, like what I described doesn't have anything to do with this. A priori, doesn't have anything to do with the objective function. But there is a global potential function which is always decreasing under this process. So here's the outcome. So what's the point of the objective function? That's actually what gives you the multiplicative weight. So if you actually put these constraints into the Lagrangian, then basically you're only willing to make progress on some constraint if when you move in the direction of some constraint, you start at the uniform measure. So now your relative entropy will be decreasing. Okay, but these exponential weights come from the fact that there's a trade-off. You're only willing to improve the constraint if the cost in increasing the entropy, the relative entropy of your function is not too large. So okay, this is okay. So you can, this has by many names, mere descent and so on. But okay, so then you do this, you do some updates. What's the end result? Okay, the end result is that there exists a function of the following form. Okay, so it's just going to that is feasible. That's not surprising. There's more, but the form is exactly what you would get from doing this exponential weight update. So sort of like here you're moving in the direction of the constraint, but exponentially. These lambda sub s's are the dual variables corresponding to each of these constraints. And okay, so you get something of this form that is feasible. So it satisfies all of the constraints. And the fact that, okay, this is where the epsilon comes in. the fact that you only move in the direction of a constraint if it's violated by some epsilon means that at every step, this global potential, we can, if you have questions, we can talk later about what it is, decreases by a definite amount, which means the number of iterations is bounded. Okay, so this gives us an additional property that the number of S such that the coefficient is non-zero, this is bounded by, okay, it's bounded by, the first thing is, okay, the first thing is we have a bunch of linear tests. Every linear test is multiplying against phi restricted to some subset. So you have to pay somehow how complex the tests are. So you have to, it's the maximum value of phi. You have to pay something for the amount of error you want. If you want less error, then you might have to go for more steps. And then what you have to, then what basically this thing is going to be the value of this potential initially. So there's some potential which starts out, and every time you make some improvement, it's decreasing, and it's always non-negative. It bounds a number of steps. That potential is bounded by the relative entropy basically by the value of the optimal solution here. So the point is we know that BI is a potential solution to this program of value at most twice log R. Right? BI has the D value of BI is at most twice log R, and certainly BI satisfies itself all of these constraints. So that gives us, so this is where we use the, okay, I guess I can write it this way. This is at most this, which, okay, so now for our sake, this is some constant depending on G. Epsilon is going to be, yes, so epsilon is also going to be, the epsilon we'll need is also some constant which depends on G. So the best way to think about this is just that this is order of log R, because this thing is twice log R. Okay? So the point is that since basically, since the initial thing we start with is not too complicated in the sense that it's fairly close to uniform distribution in this relative entropy sense, this program converges after, this gradient descent procedure converges after a small number of steps. Okay? And every step you just update by one function. So the number of sets that you see is bounded by order log R. And this implies in particular that this BI tilde, now I refer to the one that we said exists. So how many coordinates does it depend on? Well, it depends on phi sub s for order log R values of s. And each one of those phi sub s's only looks at m bits, because it's just looking at the restriction to s. Okay? So this is an order m log R Hunter. Okay? Okay, so at least the word junta has appeared. So you might be feeling really nice now, because sort of like we wanted to approximate by a junta. We wrote down this program. This principle, by the way, is that sort of this entropy maximization is very powerful. Yeah.
Sorry. How did you argue that BI tildes are different from BI? Why couldn't the solution of the optimum just be the original BI?
No, it could be, well, sort of BI tilde is not optimal here. You can analyze here the optimal solution and say something, but then you have to truncate e to the x and things. So it's so the BI tildes are not optimal. They could be themselves equal to the BIs. In fact, if BI is a junta, this is actually what you would expect to happen. So but that's okay. I mean, if BI is a junta, then the argument is already going to work. So
you get the fact that it's a junta by the fact that the lambda s's, there aren't too many.
Right. Yeah. So the sort of the dual variables occurring here are supported on a sparse set of constraints.
So did you actually solve this finding? Is that what I should think about? You have this convex program and you take multiplicative weights.
Yeah.
And you realize that it's not going to have too many lambda s's.
Yeah. You do multiplicative weights, and just if the way you set up the multiplicative weights is that basically an oracle says here's the violated constraint, and now you respond to that violated constraint, then the number of steps you do you need, in the multiplicative, in sort of this procedure, is it bounds the number of s's you see, which bounds the number of variables you look at. So the running time of multiplicative weights bounds the number of variables that this bi tilde is looking at. It starts out as uniform, which doesn't need to look at any variables. So it starts out as a zero junta. Okay. So all right. So this is exciting, except for the fact that this is really bad. Why is it bad? Remember that we want this thing to be a D junta because our phi here, it fools D juntas. Now, D is the junta degree of G, so D is certainly less than M because G is on M bits. So, okay, so this thing is much bigger than D. I mean, it doesn't even have any hope of being. So this seems really troubling. Like we wanted to get a D junta, we got an M log R junta, and D is less than M. I mean, D could be much less than M even. So this seems bad. Okay, but now let's remember what we want to look at. So we're at the end of the day we want to look at the following expression. Okay. So now we suppose our approximations are good enough that we can replace the bi's by bi tildes, and then so this is one of the terms on the right hand side of the factorization. When we would like to argue that this is non-negative. If bi tilde was a D junta, it would genuinely be non-negative. That's what we argued here, but it's not. Okay, so what can we do? Okay, so let's, here now the picture is the following. So we have, we have a kind of m bits, n bits, and then, for every set S, these sets S are of size M. So sort of, here is what one of these sets S might look like. And sort of, so when we look at this expression, this is really an expression which is going on down here on the set S. I mean, they're averaging over all of the X's, but this thing only depends on the bits inside S. So the point is that, okay, so we can just, let's write this averaging slightly differently. So let's first average over the bits inside S. And then, okay, so phi, right, the definition of this thing is phi at X restricted to S. Okay, so first we just choose the restriction. And then the averaging over the rest of them can come inside, because this thing doesn't depend on the rest of the bits. So now we have here, let's say we average over now n-bit strings, so that the restriction of the string is equal to y. Okay, so that's, we fix y here, and now we're averaging over everything outside. And here we put bi tilde of x. Okay. Okay, good. So we know that this bi tilde is an order m log r junta. Let's suppose in fact that let's just give a name to its junta coordinates. So let's say we'll give it the name, okay, J is for junta. We already use cursive J, but this is a non-cursive. Okay. Okay. So the point is, yeah. So bi tilde is a m log r junta, and let's say this is the set of coordinates on which it depends. Okay. The point is that this thing is actually a junta on Ji intersects S. This is the main. I'm claiming that what is this thing? This is a function. You can think about this as a function of y, right? This maps some y to this value, which is you average over everything outside of the set S. And this function depends on only the coordinates that bi depended on intersected with S, because we average over everything outside of S. And now you can see that we're actually in pretty good shape, because m, right, n is going to infinity. M is small. So like the expected number of coordinates of these Kunta coordinates that land in this set S is actually, actually as n goes to infinity, it becomes much less than 1. You don't even expect to get 1 there. What we really care about, though, is what happens. So the point is that when we choose an S and the size of this intersection is at most D, then this is a D junta, and this whole expression is non-negative. Right? So the only thing we care about is is the bad case when we choose a set S that has an intersection being large, and sort of you can write this out, but the probability that this is bigger than D, okay, let's write down exactly what it is, and then okay, so it's, let's see, the number of possibilities for the set is n choose m. If I have at least D things, okay, just for simplicity, let's say bigger than or equal to D. So then I should choose first, okay, I guess we should give this, okay, let's also just give this, the number of coordinates is order m log r, but let's call this number k. So, okay, so we should choose from our k junta coordinates, D of them which are bad, and then we have to choose the rest of the set S. So then from the remaining n minus D things, we will choose m minus D things. Yeah, this is actually exactly true. So I just did the counting. The total number of subsets is n choose m. If I get D things, then what I should do is just, okay, so it's, let's say, at most, I might have overcounted a bit. I did overcount a bit. I need to choose from the k junta coordinates of ji, D of them to be in S, and then the rest of them I can choose arbitrarily. I overcounted a bit if there's more than D, because then there's different ways to move the D special ones around, but it's an upper bound. And the point is that remember, okay, so this k we said is order m log r, and the lower bound we're trying to prove is something like r is n to the d. So this is like, okay, so this is sort of, you can think about this as like md times log n, and m and d depend only on g, so those are fixed constants. So the number of junta coordinates is actually quite small. So really, at least philosophically, this is like this. Okay. M is small, k is small, d is small. Basically, the probability that we get more than d things is going like n to the minus d. The probability for one bad coordinate to fall there is like maybe, if we were really, okay, if we were going to be really precise here, then, really precise means that it's actually true. Then if we put here the log n, it would be true. So we have log n junta coordinates. The probability that one of them falls there is log n over n. The probability that d of them is like log n over n to the d. Yeah.
Sorry, could I ask you to repeat your argument for why that's a junta on Ji and like that?
Yeah, good question. First of all, it's a function. It's a function only of y, right? We average when I say it's a junta, we're talking about sort of, we take some y and then we compute this thing, which is you fix the bits inside S and you average over everything outside. So it's certainly only a function of this y. It doesn't depend on anything. We're averaging over everything else, so it cannot depend on those values. So it certainly will only depend on things inside S, because y is only looking at things inside S. And itself only depends on things in Ji. So that's the argument, that it only depends on it only.
So just by taking, so supposing S does not intersect Ji at all. Right. So then.
This is a constant function.
Right. So then, oh, I see.
In fact, it's the constant one function in that case. Yeah. Yeah, so I mean, you just, yeah, here's ji, here's s. You know, changing a bit here doesn't change the value at all because, I mean, you can change it, but then we'll average over both values in this expression, so it doesn't matter. Changing a bit here doesn't affect the value of bi because bi doesn't depend here. So only the changing the bits in here affect the sort of affect the value of the function. Okay, and then this is, I mean, this was just basically, yeah. I mean, naively you would say, well, the probability for one of these log n coordinates to fall, to fall in this set of size m. M is like a constant. That's the point. It's a constant depending on g. Is like log n over n. The probability for it to happen d times is approximately like this. And of course, you have to count the number of ways it can happen. But all of that counting involves, again, only some constant depending on m and d. So sort of, okay. So this should not be hard to believe. You need d unlikely things to happen for this to occur. So the probability is like n to the minus d. Yeah. So and then the last thing one needs to check is like what price does. Okay. So sort of we're analyzing this expression. Okay. Which we can write this one this way. So whenever this is less than d, this expression is not negative and we're happy. Sometimes we'll get unlucky and the set and the intersection size will be bigger than d. And then what do we pay? Well, I mean, so then in some sense, okay. So I'll just write it down formally, what we pay. And it's the end of the proof. So basically, what we're arguing here is that this bi tilde x is at least, so most of these things are, for most values of s, this is giving us a 0 contribution. For some values, it's giving us a negative contribution. Okay, with some very small probability, let's say we pay the worst possible thing, which is the L infinity norm of the AI. I just say that almost every time we get something non-negative, with very small probability we get something negative, and I'll just assume that you had to pay the worst possible cost for this. Okay. So the last thing we need is some fact. I mean, which is okay. So the fact is okay, it's trivial, which is that okay. I wrote the sum, but each of these individually, like look at the expression there. Every one of those things is bounded by the magnitude of g because it's appearing on the. Okay, so yeah, I mean, okay, I claim that this is at most r times the magnitude of g. I guess actually, strictly speaking, to see that, you should look at the expression for this matrix. Take x, take expectation of both sides with respect to x. Now all the bi's have expectation 1. So you just get that the sum of these AIs is at most the left-hand side, which is bounded by the maximum value of g. Okay, so every one of these AIs is bounded by the maximum value of g. So there's r of them. So the sum of them is r times this, right? And this is some constant. So this is like order of r. And so now you see that the total error. So the error for one term is possibly the maximum value of g, but this happens for all r different terms. Okay, so I guess okay. So the total error we incur for this probability of having an unusually large intersection is order r times something which is approximately n to the d. So this is sort of approximate, and this is much less than 1 when r is much less than n to the d. And the point is that when we make this error small enough, then the separation between the two sides still holds. So the right-hand side is not, when we evaluate this kernel on both sides, the right-hand side is not, it might be negative, but it's only a tiny, tiny bit negative. Okay? And as long as we make that tiny bit negative, sort of some very small constant, we still have a separation. Okay. So that's the, so the point is that this is a contradiction, right? So if we make the error too small, then we have a separation between the two sides. We conclude that the rank is up to, actually, if you look, we actually did slightly better than I claimed before, because here you can put greater than or equal to d plus 1, actually, and you will get d plus 1 and so on. But okay. But the point is this, I mean, if you go through the details there, there's nothing, sort of no serious details, then indeed you conclude that the rank has to be very large. And now I realize that I lied to everyone at some point, because I said that there's only one place we're using the rank, which was when we bounded the BIs. But then we used it again. So actually, there's two places where you use the rank, and it makes sense. You use it once for the BIs and once for the AIs. Right. So if you sort of import this inequality for the AIs and an absolute value bound on the BIs, then you can throw away the number of terms. But you need to have some sort of, right? In some sense, this says that the left-hand side of the factorization, these AIs cannot concentrate too much on, they cannot be too complicated, right? So the L infinity norm of the B's bounds them, the L infinity norm of the AIs bounds them, and you put them together. That's the argument, okay? And this step here, this is a common sort of thing. This goes by the name of like a random restriction argument, right? We got some non-trivial approximator, and then we use the fact that if this number is much less than n, the trivial junta. So we use the fact that if we have a small junta and then we look at a random subset, then actually the size of the junta shrinks dramatically. So if you think about this in terms of relaxations, what we did was we said, if we have a small linear programming relaxation, a small linear programming characterization of the cut polytope, then if we look at a random subset of the variables, we can find on them a Shirali-Adams characterization of the cut polytope on graphs of smaller size. Okay, and then we have a lower bound, on the junta degree, which is a Shirali-Adams lower bound. So that gives us a lower bound on the size of general, of these general linear programs. Okay, so I think we have 15 minutes, right, to address the main topic. So now the intro is done. Now, but please ask if you have some questions there. The overall thing to take away is that we really, we work a lot, we worked here in the dual setting, so it's not completely necessarily clear what's going on. We basically said that we can, if we take a linear program that captures the cut polytope that has a small number of constraints, then on a random subset of the variables, say we choose root n of the variables, and we say, okay, well, now this program, if I restrict it to root n of the variables, gives me some characterization of the cut polytope on root n variables. Then the fact there's a small number of constraints means that this restriction will actually, every constraint will be sparse. This is sort of a Shirali. Every constraint will depend on only a few variables in an analytic sense, because there's errors and all kinds of things going on here. It would be really nice if somebody can make that, if somebody wanted to try and make that more concrete. And it might also bypass many, might make progress on the open problems. To really say that you can start with a general relaxation and derive from it a Shirali-Adams relaxation, which is just one where every constraint depends on only a few variables. So a few vertices of the underlying graph. Okay, so we can do this. We can give I can tell you. Now, suppose you want to go now to, okay, so first let me tell you what is the model for semi-definite programs, and then I'll give you the dictionary between the two proofs. Okay, so we have, So we were studying this. So this is what you could call a polyhedral lift size of P. It corresponds to capturing P by the feasible region of some linear program. Okay? So if we want to think about capturing a polytope P by the feasible region of some semi-definite program, well, we should say what do the feasible regions look like? Okay, so if you define this to be this is the set of symmetric real D by D matrices with all non-negative eigenvalues. Okay, so you can think about this naturally as embedded in, I don't know, again, let's say D squared dimensions. Okay, so this is the positive semi-definite cone, and then let's let V be some affine subspace. So affine just means that it's a linear subspace, but then we can shift it. So, okay. Then the objects we care about for semi-definite programs are exactly this thing. This thing is called a spectrahedron. Okay, so these are precisely the feasible regions of semi-definite programs. And let's even of dimension D. Okay, so now the corresponding parameter in the semi-definite programming setting is we can call it, let's say, gamma sub STP of P is the minimal dimension of a spectrahedron that projects linearly. So that's the same definition as for a lift, but now we allow you to use such objects instead of polytopes. Dimensional spectrahedron that that linearly projects to P. Okay, so this is in the same way that this captures, by and large what we mean by linear programming, this does the same thing for semi-definite programming. Okay, so this was, this is at least the definitions. And so now, yes, let me state a theorem just so that, okay. So one can use, okay, well, for the length of time, I'll give us all initials. So this was actually just, just proved at the beginning of the year that these kind of techniques can give lower bounds for semi-definite programming size. So some constant to the n to the 2/11, say. Okay. So one can prove one can prove lower bounds on this on the size of semi-definite programs for the cut polytope by following what we already saw. And I guess the most important thing to stress about these, okay, so how did we do it in the setting of here? Well, we first identified a canonical family of lifts. Okay, so these were the Charley-Adams lifts, or in our setting, they were they were these these lifts corresponding to the cone of D juntas for some, so K juntas for some K. So if you do the same thing in this setting, you get also a notion of degree. So okay. So in the polyhedral setting, basically you go through the same series of steps. We had this junta degree. The analog is the sums of squares degree of a function, which is the following. Okay, so we have a function which is non-negative, and we can ask ourselves, is it possible to certify this non-negativity by writing f as a sum of squares? Okay, so when I write something as a sum of squares, I definitely give you an argument that it's non-negative, because squares are non-negative over the reals. So now the degree is it's the minimum D such that I can write f as a sum of pix squared, and each one of these is a polynomial of degree at most d. So this is the sum of squares degree. Okay. Right. So the Hünte degree corresponds to certifying non-negativity of f by writing it as a non-negative combination of Hüntes. The sum of squares degree involves certifying non-negativity, writing as a non-negative sum of squares of polynomials of degree at most d. And you can, here's an easy exercise just to see that this is indeed a more powerful notion. So the sum of squares degree is always smaller than the Hünte degree. If you can write it as Hüntes, then this is, here everything I'm saying is over 0, 1 to the n. This is not necessarily true anymore not over 0, 1 to the n, but over 0, 1 to the n, it's true. Okay, so we have, so now, the dictionaries, we have, we have gamma, and we have gamma STP. Here we have Hünte degree. Here we have sum of squares degree. Okay. Here we had a sort of a general, the way we related these things is that, I see. Yeah, so okay, I guess I could have done this before. I mean, the notion of rank is probably the most important thing here. Here we had non-negative rank, which captures this polyhedral extension complexity. And it turns out that there is a notion over here that captures exactly this, the size of a spectral hedral lift. And so let me define it very briefly, and then we're close to stopping. Okay, so I'll remind you that the non-negative rank is the minimum over all R, such that I can write Mij as the inner product of, let's say, AI and Bj, where these are, okay, if these were just vectors in R dimensions, then I have just written down the definition of rank. If I take these to be non-negative vectors in R dimensions, then that's really the non-negative rank. And so now the positive semi-definite rank has just a very nice analogy. We're going to write everything is the same, except now, okay, instead of positivity, we're just going to require positive semi-definiteness. Okay, so we want to be able to write Mij as trace AI Bj. I'll explain that in 1 second, where the AI and the Bj are now positive semi-definite R by R matrices. And these are really so this is the Frobenius inner product, but the way to think about this inner product is that these are just R by R matrices. This is just the, if you think about them as R squared dimensional vectors, this is the inner product. So in fact, this expression is really the same kind of thing as this expression. The only thing we really changed is the domain. So in fact, maybe even a better way to say it, this is the same. This is the same as this if we require these matrices to be diagonal. So if these matrices are diagonal, we get non-negative rank. But if they're not diagonal, we get some possibly stronger notion, because the fact that they don't have to be positive, they just have to be positive semi-definite, gives this more expressibility. Okay, so that's the, and there is a theorem here, which was observed by a couple of groups, although the main credit goes to Yannakakis because it's a straightforward generalization of his theorem. But the theorem is just that we have the same correspondence. So if we look at the non-negative rank of some slack matrix of P, then this is exactly equal to the semi-definite extension complexity. of P. So we have the same correspondence that to think about this, we can think about factorizations of slack matrices, but now not into non-negative vectors, but into positive semi-definite matrices.
So the slack matrix is just the extreme points and constraints?
Yeah, it's what we defined before. So it's the extreme points and constraints. But more than that, I mean, for instance, for the cut polytope, we went from extreme points and constraints to certifying, non-negativity of quadratic functions on the hypercube. So the same thing works here. So I just want to say okay. So what we eventually got here was we tried to certify functions by writing them as some non-negative combination of a small number of BIs. This was sort of if we use juntas, we got a specific kind of factorization. But in general, if R was a non-negative rank, it corresponded to be able to certify positivity of all of the functions in our family, all these quadratic multilinear functions, by writing them as non-negative combinations of some small number of BIs. And the corresponding thing here is to take so let's call it to take a subspace of polynomials, polynomials on R Rn, with the dimension of the subspace being R. And then the kind of certificates you can generate are, we're curious, can we write F as a sum of squares where all of these polynomials lie in a subspace? Right. So a rank R factorization, or corresponded to having R functions, and we tried to write every one of the inequalities we care about as a non-negative combination of those functions. In the SDP setting, it corresponds to having an entire subspace of functions, so a subspace of polynomials. And now your certificate can be writing your function as a sum of squares of anything from that subspace. So this is one reason why it was somewhat difficult to extend things to the PSD setting, because, I mean, the trivial arguments you might start doing, which this were the early days, to say, okay, well, maybe I can take exponentially many functions in R here and sort of discretize this subspace and try to do something. And this is, well, that's as you might expect, that's sort of hopeless. I mean, it doesn't. If you start having exponentially many functions, then well, things turn out to be not so good. But okay, so now I can say that we're going like a couple minutes over, but this is really the last thing. So what we said here was that we can approximate. Once we have an expression like this, then we can approximate these things by juntas. And the same thing is going to happen here. That basically we'll say that we can approximate these things by, in the same kind of sense, by low-degree polynomials. And then here, the approximation wasn't quite good enough. We had to use random restriction to get a much smaller junta. But now the same thing works over here. You'll get some polynomial of moderately low degree. And then upon random restriction, in expectation, the degree will shrink considerably. So the one tool that we sort of didn't specify, and I'll say it in the final line here, is to do these, to approximate these BIs, we sort of did this, we followed this kind of max entropy property, which is that we thought about these BIs as probability distributions. Then we said, okay, here are the constraints we care about. Let's maximize the entropy subject to those constraints. And we got a simpler, we got some approximator which would sort of satisfy the constraints but was simpler. The corresponding thing here is actually, it's also max entropy, but now it's, now instead of having classical probability distributions, what comes up here are quantum states. So instead of classical probabilities, you have quantum probabilities. But there is a notion of entropy for positive semi-definite matrices, which is very beautiful and miraculously satisfies many of the properties of classical entropy. And if you use this connection, even that part of the proof goes through in a very similar way. Okay? So that's the, okay, and I will say that this is sort of discovered, this was discovered in some sense backwards. So we had some method here, and then by figuring out what's going on here, we can come back and make the correspondence very clean. It wasn't so clean to start with. Okay, but that's it. I mean, the punchline for how to take what we did and go to the SDP setting is just that. Okay, it sounds scary, so it sounds like a horrible punchline. But basically, everything classical has a quantum counterpart, and by the sort of the beauty of the universe, somehow these notions translate in a way where sort of there's a fairly direct correspondence between all of the steps in both settings. Okay, let me stop there.
Thank you for these nice lectures. Looks like to book you in for some more post-intro material for next week if you come back. Any final questions?
Teach.
So do these arguments say anything about separation? Like, can you use these to somehow say that you can separate over the mind, like these modes or something?
No. So, right. So the one facet of say mathematical programming that these extended formulations don't capture is the ability to solve exponential linear programs, say with exponentially many facets. Okay, not by anterior point, but say by using ellipsoid method and separation oracles. And there is no, as far as I know, nice model that captures sort of separation oracles. It's very difficult to capture them without getting arbitrary polynomial time computation. So yeah, so this is the one thing they don't capture. So for instance, I was going to say it, but we're way past time. Rothfuss proved that the matching polytope has exponential extension complexity. So there's no small linear program. But of course, I mean, this is, we can solve matching in polynomial time, right? So this, so one nice way of saying what you're asking actually in a more like hands-on way is this: can we, right now these methods don't distinguish between the matching polytope and the traveling salesman polytope. So it would be nice if there was something that was able to give distinguish the two. I mean, there's lots of intuitions for why they're different, but they don't fit. There's not a nice model that captures it. Yeah, once you try to start formulating things, I mean, linear programming is sort of P-complete in some sense. So once you start allowing okay, what does it mean? But once you start allowing yourself to have sort of arbitrary separation oracles, it becomes very, it becomes very difficult not to get all polynomial time computation. And one could argue, in fact, that maybe even separation oracles are not linear programming. But okay, let's not do that. Yeah. And by the way, the big open question here is, we have no idea what is the size of the smallest semi-definite programming formulation of the matching polytope. And the reason is that, as I said, these techniques only seem to work over 0, 1 to the n. And once you go to, say, the matching polytope, well, you're not on 0, 1 to the n anymore. And it seems that some substantially new ideas are needed. Or that maybe it has a small STP. Who knows? But yeah.
You asked that P is not an exact projection, but an approximate projection. Would the same techniques possibly work?
Right. So as you saw, at the end of the day, we're doing analysis. We're doing, everything is analytic. So this works for approximate lifts, except now you have to be careful to keep track of, the error terms. And in particular, the thing that makes the error terms unwieldy is right this separator, right? This phi that was separating us from non-negative juntas. We just said that there's some arbitrary separator. But if this separator is not smooth, if it can take very large values at places, then it ruins the analysis parts of the proof. So to apply it to the approximation setting, you have to get some bound on the L infinity norm of this separator. And so it works, but then it only goes up to size linear programs of size n to the log n. And past that, we don't know. And there's, yeah.